At 6:37 on the morning of January 28th, 2022, a bridge in Pittsburgh fell down. Not collapsed in the sense of gradual failure. Not buckled under some extraordinary event. No flood, no earthquake, no vessel strike. The Forbes Avenue Bridge over Fern Hollow Creek simply gave way on a Tuesday morning in winter, taking with it a Pittsburgh Regional Transit bus, 4 cars, and the 9 people inside them. The bridge fell approximately 100 feet into the park below. 4 people were injured. By some margin of luck, and by a specific documentable fact, nobody died. That morning, Pittsburgh's schools were running on a 2-hour delay because of snow. The bridge typically carried more than 14,000 vehicles a day. At 6:37 a.m. on a normal school day, it would have been crowded. It was not a normal school day. The National Transportation Safety Board Chair, Jennifer Homendy, would later note that the delay almost certainly reduced the number of people on the bridge when it fell. That is how close the margin was. Not engineering, not redundancy, a snow delay. The bridge was 447 feet long. It had been carrying Forbes Avenue over the north side of Frick Park, connecting 2 Pittsburgh neighborhoods, Squirrel Hill and Regent Square, across a deep wooded ravine. It was built in the early 1970s. It was, at the time it collapsed, more than 50 years old. Rescuers rappelled into the ravine. Others formed a human chain to reach the transit bus, which had come to rest at the bottom of the drop, still carrying passengers. The morning was dark. It was still snowing. Within hours, the National Transportation Safety Board opened an investigation. What they found over the next 2 years was not a mystery. It was a record. Inspection report after inspection report, going back years, had flagged the bridge's deteriorating drainage, its corroding steel legs, the water pooling at the base of its supports. Maintenance recommendations had been issued. The city had not acted on them. The contractors hired to conduct safety inspections had not followed federal guidance. They had failed to identify the bridge's fracture-critical components. They had calculated its load capacity incorrectly. Had they done the math right, the bridge would have been closed before it ever fell. The Fern Hollow Bridge collapse should never have happened, Homendy said at the NTSB's final hearing in February 2024. This bridge didn't collapse just by an act of God. It collapsed because of a lack of maintenance and repair. That same day, January 28th, 2022, the morning the bridge fell, President Biden was scheduled to arrive in Pittsburgh to promote the Infrastructure Investment and Jobs Act, which Congress had passed 2 months earlier. The bill included $5.5 billion annually for bridge repair. He gave the speech a few miles from the wreckage. The Fern Hollow Bridge is not an outlier. That is the thing worth understanding. The city of Pittsburgh did not fail in some spectacular or unusual way. It failed in the ordinary way that underfunded municipal infrastructure agencies fail. Too few staff, too little budget, too many recommendations that stayed on paper. The conditions that produced that collapse exist in hundreds of cities, across thousands of bridges, in every state in the country. There are 623,218 bridges on public roads in the United States. On any given day, they carry close to 5 billion vehicle trips. Most of them are fine. A meaningful number of them are not. 623,000 bridges. That is the number the Federal Highway Administration tracks In the National Bridge Inventory, every structure 20 feet or longer on a public road in the United States, from the interstate crossings over major rivers to the concrete culvert bridges on county roads in rural Montana. Every one of them is inspected, rated, and assigned a condition score. Every one of them carries something: cars, trucks, school buses, ambulances, freight. Together they carry close to 5 billion vehicle trips every day. The condition rating system runs from 0 to 9. A 9 is a new bridge. A bridge rated 6 or above is in good condition. Its primary components are performing as designed, showing normal wear for their age. A bridge rated 5 is in fair condition. It has deteriorated past the point of routine wear. The components are showing signs of aging, but there is no critical deficiency requiring immediate action. A bridge rated 4 or below on any primary component, deck, superstructure, substructure, or culvert, is in poor condition. That means serious deterioration. Advanced section loss in steel, significant cracking or spalling in concrete, undermined or settled foundations. The structure is still standing, still carrying traffic in most cases, but it has crossed a threshold. It requires close monitoring. It often carries posted weight limits. It needs rehabilitation or replacement, and it needs it on a timeline that is already shortening. Think of it as the difference between a car that needs new brakes eventually and a car where the brake pads are metal on metal. The second car still stops, until it doesn't. As of the most recent federal data, approximately 6.8% of the national bridge inventory is in poor condition. The American Society of Civil Engineers puts that number at over 46,000 bridges. The Federal Highway Administration's June 2025 National Bridge Inventory Count, which uses a slightly narrower definition covering public highway bridges but excluding some culvert structures, puts the figure at approximately 41,685. The difference comes down to what gets counted. The condition it describes is the same. Either way, the number is enormous, and it is not the most important number in this section. The most important number is 49.1%. Nearly half of all bridges in the country, 49.1%, are currently rated in fair condition. Not poor, not failing, fair. They are the bridges that have not yet crossed the threshold, that do not yet carry load postings, that do not yet appear in the crisis statistics. They are also the bridges that are actively deteriorating. A bridge in fair condition is a bridge on a trajectory. The question is not whether it will reach poor condition. The question is when, and whether the money to intervene will arrive before it does. The pattern shows up most clearly on the interstate system, which was built to move the nation and remains its most critical freight and commuter network. 1 in 3 interstate highway bridges, 18,177 structures, currently has identified repair needs. These are not back road crossings over seasonal streams. These are the bridges underneath the traffic that moves the American economy. The American Society of Civil Engineers gave bridges a C in its 2025 infrastructure report card. That grade has not changed since 2021. The overall national infrastructure GPA rose for the first time in the report's history, crossing from a C- to a C. Bridges held steady. In the context of this inventory, steady is not reassuring. A C means the system is functional. It means it is not in immediate crisis. It also means that nearly half the structures in it are in a condition category one step above the one that generates headlines. The average age of a bridge in the United States is 47 years. That number matters because of what bridge designers assumed when they drew their plans. The standard design life for bridges built in the mid-20th century was 50 years. Not 47, 50. The country is not approaching that threshold. For a very large portion of this inventory, it has already passed it. What happens to a bridge that keeps carrying traffic past the life it was designed for is the subject of the next several hours. The short version is this. It depends entirely on what has been done to it in the intervening decades. And for too many of these structures, the answer to that question is not enough. In 1956, Congress passed the Federal Aid Highway Act and committed the United States to building the most ambitious road network in human history, the interstate system. 41,000 miles of controlled access highway connecting every major city, crossing every significant river, threading through mountain passes and across coastal plains. It would take decades to finish. The bridges that carry it, thousands of them built through the late 1950s, the 1960s, and into the 1970s, were engineered to a specific set of assumptions about load, volume, and time. Those assumptions are now wrong. Not wrong because the engineers made errors. Wrong because the country those engineers were designing for no longer exists. The traffic volumes are different, the vehicle weights are different, the climate is different, and the bridges are still there, carrying all of it on steel and concrete that was specified for a world that has since changed around them. The standard design life for bridges built under mid-20th century guidelines was 50 years. That was the planning horizon, the period over which the structure was expected to perform without fundamental rehabilitation, assuming normal maintenance was performed. Modern AASHTO bridge design specifications use 75 years as the standard service life. That revision happened because engineers learned over decades of watching real bridges age that 50 years was optimistic for structures carrying the loads and traffic that American roads produce. The revision did not retrofit the bridges already built. Approximately 45% of the bridges in the national inventory have already exceeded that original 50-year design life. Nearly half. They are still in service. Many of them are on the interstate system, which means they are carrying the heaviest, most frequent loads in the country. The freight corridors, the commuter routes, the emergency response networks. They are doing this on structures that, by their own design parameters, are operating in overtime. The age distribution tells the story directly. Bridges currently rated in poor condition average nearly 69 years old. Bridges rated in good condition average 44 years old. That is a 25-year gap between the bridges that are failing and the bridges that are not. It is not a coincidence. It is the design life asserting itself across the entire inventory simultaneously, because an entire generation of bridges was built within a compressed period, and that generation is now aging together. Consider what the designers of a bridge built in 1965 were working with. The trucks on American roads in 1965 were lighter than the trucks on American roads today. Freight vehicle weights have increased as the economy shifted toward just-in-time logistics, as container shipping grew, as the pressure to move more goods faster per trip intensified. The bridge built for the legal load limits of 1965 is now being asked to carry vehicles that in some configurations, test or exceed those limits. The deck that was sized for the traffic counts of a mid-sized American city in 1965 is now carrying the traffic counts of a city that has grown for 60 years. The bridge does not know any of this. It carries what it is given. What it does, quietly, over years, is accumulate the cost. Every load cycle, every truck crossing, every freeze-thaw season, every summer of thermal expansion, puts a small withdrawal from an account that was open with a fixed balance. The engineers set that balance in the design. They estimated how many cycles the steel could absorb before fatigue became a factor, how many winters the concrete could survive before the chloride worked its way to the rebar, how much settlement the foundations could tolerate before the geometry of the structure changed in ways that mattered. They made those estimates for the loads and the climate they knew. The loads have grown. The climate has shifted. The account is drawing down faster than the original math projected in bridges across the country, all at roughly the same time. The interstate system's bridges were not built one by one over a century. They were built in a wave between roughly 1958 and 1975. That wave is now reaching the end of its design life as a wave. Not as isolated failures scattered across decades, but as a broad, simultaneous reckoning with the limits of what was built. The Fern Hollow Bridge was built in the early 1970s. It was 50 years old when it fell. That is not a coincidence either. A bridge inspector standing on a deck in Ohio pulls back a chunk of concrete the size of a dinner plate. Underneath it, the rebar is brown, not surface rust. The kind of oxidation that happens to any exposed steel after a wet season. This is section loss. The steel bar that was cast into that deck in 1968 at a specified diameter is now smaller than it was. The concrete that was supposed to protect it, to keep the chloride out, to maintain the alkaline environment that holds corrosion at bay, has failed at that spot. The rebar is thinner than the engineer assumed when he calculated how much load that deck could carry. That inspector records a condition rating. The scale runs from 0 to 9. 0 is a bridge that has failed. 9 is new construction. The range that matters most for understanding what the national inventory actually contains sits between 4 and 6. The territory where the decisions get made and the money either arrives or doesn't. A bridge component rated 6 is in satisfactory condition, some minor deterioration, nothing that affects structural capacity in a meaningful way. A component rated 5 is showing moderate deterioration. Section loss beginning in steel, cracking visible in concrete, somewhere that bears watching. The structure is sound, the trajectory is downward. A component rated 4 is different. 4 means serious deterioration. The FHWA defines it as a condition where the primary structural element has advanced section loss, deterioration, or cracking that warrants a high level of concern. When any primary component, deck, superstructure, or substructure, hits 4, the bridge crosses into poor condition. It does not mean the bridge is about to fall. It means the margin between the load the bridge is carrying and the load the bridge can safely carry has shrunk to a point that requires action. The margin is the thing. Every bridge is built with reserve capacity. The difference between what it is designed to carry and the point at which it actually begins to fail. A new bridge has substantial margin. A bridge rated 4 has much less. Not 0, but less. and less margin means less tolerance for the unexpected. The overweight truck that runs the scale, the flood that scours the foundation, the hard winter that accelerates the corrosion by another season. What that looks like in practice depends on which component has reached 4. A deck rated 4 is a surface problem with structural implications. The deck is the part drivers touch, the roadway surface, and the concrete slab beneath it. Road salt applied in winter dissolves into water and works its way through cracks in the deck surface. It reaches the rebar. Chloride ions break down the passive oxide layer that protects steel in an alkaline environment. Corrosion begins. As the rebar corrodes, it expands, which spoils the concrete from the inside, splitting it from beneath, creating the chunks that fall, the potholes that form, the exposed steel that rusts openly in the rain. A deck in this condition is carrying traffic on a surface that is no longer the surface the engineer designed. The load path has changed. A superstructure rated 4 means the beams and girders and trusses that actually span the gap are deteriorating. These are the primary load carrying members. Section loss here is not a surface problem. It is a reduction in the cross-sectional area of steel that is doing the fundamental work of holding the bridge up. An I-beam that was specified at a certain web thickness in 1971 and has lost material to corrosion over 50 years is a different beam. The calculation the engineer ran in 1971 assumed a full cross-section. The beam that exists today is not that beam. It is thinner. It carries less. The math is wrong, not because anyone made an error, but because the object the math described no longer exists. A substructure rated 4 means the piers and abutments, the elements that transfer load from the bridge into the ground, are compromised. This is often where flooding does its work, or where settlement has changed the geometry of the structure in ways that redistribute load to points not designed to receive it. When any of these components reaches 4, the bridge typically receives a posted weight limit, a sign at each end. Vehicles over a certain tonnage must use another route. That sign is not a minor inconvenience. A weight-posted bridge means that the school district has to reroute buses. It means that the fire department has to account for it in response routing. In some rural areas, the nearest alternative crossing adds meaningful minutes to an emergency response. It means that agricultural equipment and logging trucks and construction vehicles cannot use it, which in rural counties with sparse road networks can mean long detours or simply unserved access. The bridge is still there. It is just no longer doing what a bridge is supposed to do. There are thousands of weight-posted bridges in the United States. Many of them have been posted for years, some for decades, posted and monitored, which means inspected on a schedule and watched for further deterioration, while the funding needed to rehabilitate or replace them either waits in a queue or does not yet exist. The concrete chunk on the deck in Ohio goes into the inspector's report. The rating is recorded. The condition is documented. What happens next depends on a budget process, a maintenance queue, a state DOT's prioritization formula, and a federal funding structure that is, by every current measure, providing less than half of what elimination of the backlog would require. The chunk came off a bridge that was there yesterday. It will be there tomorrow. Most of the time, that is fine. What is supposed to happen before a bridge falls? The Federal Highway Administration has an answer to that question. and it is codified in the National Bridge Inspection Standards. A regulatory framework that has governed the safety inspection of public highway bridges since the early 1970s. Under those standards, every bridge in the national inventory must be inspected at minimum once every 24 months. Fracture-critical bridges, those whose primary tension members have no structural redundancy, must be inspected on that same 24-month cycle without exception. Some bridges in demonstrably good condition can, with explicit FHWA approval, be placed on a 48-month routine inspection interval. The standard is not voluntary. It applies to every state, every federal agency, every tribal government maintaining bridges on public roads. A routine bridge inspection is a physical, hands-on process. An inspector walks the deck, examines the superstructure, looks at the substructure from below, or from a boat if the bridge crosses water. For fracture-critical members, the inspection must be close enough to touch. Not a visual survey from a distance, but a direct examination of the specific components whose failure would bring the structure down. The inspector assigns condition ratings to each primary element. Maintenance recommendations go into the report. The report goes to the bridge owner, the state DOT, the county, the city, whoever is responsible for that structure. The Fern Hollow Bridge was inspected on that cycle. The reports came back with findings, drainage issues, corrosion, recommendations for maintenance and repair. Year after year, the inspection record documented what was happening to that bridge. The clogged drains on the structure were allowing water to run down the bridge's steel legs and accumulate at their base, along with debris. In normal weathering steel, the uncoated steel used in that bridge's construction, exposure to wet and dry cycles produces a stable protective rust layer called a patina. That patina is not a defect. It is the intended protection mechanism. It seals the surface and slows further corrosion. But patina formation requires those wet and dry cycles. A steel leg sitting in pooled water at its base, in contact with accumulated debris that holds moisture, never dries. The patina never forms. Instead, the corrosion continues, unprotected, season after season, eating into the cross-section of the steel. The NTSB investigation found corrosion and section loss on all 4 of the bridge's legs. Visible holes had formed in the steel. The southwest leg's transverse tie plate, a fracture-critical component, had deteriorated to the point of failure. The inspection reports had seen this coming. Maintenance recommendations had been issued to the city of Pittsburgh repeatedly. The city did not act on them. Pittsburgh's own communications director would later acknowledge that the city did not have sufficient personnel or budgeted funds for bridge maintenance or repair in the years leading up to the collapse. The recommendations sat in the record. That is one failure. The second failure runs deeper. The contractor's Pennsylvania Department of Transportation hired to conduct inspections on behalf of the city were not following federal guidance. The NTSB found that they failed to identify the bridge's legs and the transverse tie plate as fracture-critical components. Because those elements were not identified as fracture-critical, they did not receive the more intensive, hands-on examination that fracture-critical inspection requires. The inspectors were looking, but not at the right things, with the right protocols at the right level of scrutiny. The third failure is the one with the most direct consequence. The load rating calculations, the engineering math that determines how much weight a bridge can safely carry, were wrong. The contractors had not correctly accounted for the holes and section loss in the bridge's legs. They had used the wrong factor for estimating the leg's ability to resist buckling. They had miscalculated the weight of the asphalt surface on the deck. The NTSB was unambiguous. Had the load rating been calculated correctly, accounting for all three errors, the result would have required the bridge to be closed to traffic. The Fern Hollow Bridge should not have been open on the morning of January 28, 2022. It was open because the system that was supposed to catch its deterioration produced the wrong answer at every stage, where the right answer could have changed the outcome. This is not an argument that the National Inspection System is broken. It is an argument about what the system can and cannot do. It can catch visible deterioration if inspectors are following correct protocols and bridge owners are acting on findings. When either of those conditions fails, and Pittsburgh demonstrated that both can fail simultaneously, the system does not compensate. There is no redundancy in the oversight chain any more than there was redundancy in the bridge's steel legs. There is also something the inspection system was never designed to catch at all. Routine inspections assess the current condition of existing components. They evaluate what the steel looks like today, what the concrete looks like today, what the ratings are today. They were not designed to go back to the original engineering drawings and ask whether the calculations made in 1962 or 1967 or 1971 were correct. In Minneapolis in 2007, that question turned out to matter more than anything an inspector could have seen by walking the deck. 40 years of inspections found nothing wrong with the I-35W bridge. That is not an indictment of the inspectors. It is a description of what routine bridge inspection is designed to do and what it is not. Inspectors walk the structure. They rate the condition of what they can see and touch. They assess deterioration, section loss, cracking, settlement. They do not, as standard practice, go back to the original engineering drawings and verify that the calculations made during design were correct. That is not what the inspection program was built for. The I-35W bridge carried Interstate 35W across the Mississippi River in Minneapolis. 8 lanes, 1,907 feet long. It opened in 1967 and became, over the following 4 decades, one of the most heavily traveled crossings in Minnesota, carrying approximately 140,000 vehicles a day, the third busiest bridge in the state. It was a deck truss design, which means its load carrying capacity depended on a system of interconnected steel members forming a series of triangles across the span. At the points where those members connected, large steel plates transferred the forces from one member to the next. Those plates are called gusset plates. They are not secondary hardware. They are primary structural components. The joints in a system where every member is either in tension or compression, and where the forces passing through those joints are enormous. A gusset plate is to a truss bridge what a knee is to a leg. The point where the load changes direction, where the force from one element is transferred into another. If the knee fails, the leg does not redistribute the load. It collapses. The gusset plates on the I-35W bridge were designed by the engineering firm Sverdrup and Parcel and Associates in the 1960s. When the NTSB investigation reconstructed the original calculations after the collapse, it found that the plates at a critical node, designated U10, had been undersized from the day the bridge was built. Plate U10 was half an inch thick. The forces the bridge actually experienced required a plate 1 inch thick. The error was in the original drawings. It had been there since 1967. 40 years of inspections had not caught it because 40 years of inspections had not been looking for it. Checking the accuracy of original design calculations was not standard practice. The inspection standards were not written to do that. For 4 decades, the bridge carried its load on a component that was operating above its actual capacity. The margin was thin from the beginning. What happened over those 40 years was that the margin got thinner. Every time the deck was resurfaced, a routine maintenance operation, the kind done on bridges across the country, a new layer of asphalt went down. Each layer added weight. Over the bridge's lifetime, those accumulated resurfacings increased the total weight of the structure by approximately 20%. The bridge was heavier than the engineers who designed it had planned for. The gusset plates were carrying more than the engineers who sized them had calculated. Neither fact was visible in a routine inspection. Neither fact appeared in a condition rating. On August 1st, 2007, the deck of the I-35W bridge was under construction. A section of lanes had been closed for resurfacing work. Construction equipment and materials had been staged on the bridge. Approximately 262 tons of it positioned in the closed lanes directly above the main span. Directly, as the investigation would later determine, above the U10 node. At 6:05 in the evening, during the rush hour that was flowing through the remaining open lanes, plate U10 failed. The bridge was a fracture-critical structure. That term has a precise engineering meaning. A bridge whose primary tension members have no structural redundancy, meaning that if a critical member fails, there is no alternative load path. The load does not redistribute. The adjacent members do not pick it up. The structure simply loses the connection it depended on, and the geometry that was holding everything in equilibrium is gone. Once U10 yielded, the collapse took seconds. About 1,000 feet of deck truss fell. The main span dropped 108 feet into the Mississippi River, a 15-foot deep river. 111 vehicles were on the portion of the bridge that came down. 13 people died. 145 were injured. The replacement bridge was designed on an accelerated schedule and opened 14 months later, in September 2008. It was built with redundancy. In the immediate aftermath of the Minneapolis collapse, federal officials ordered emergency inspections of steel truss bridges across the country. The inspection program was not built to catch what had failed in Minneapolis. The emergency inspections were looking for visible deterioration, which is what the program was built to find. The design error that killed 13 people had been invisible to the inspection system for 4 decades, not because the inspectors failed, but because the system had never been asked to look for that particular thing. Minneapolis and Pittsburgh represent 2 different ways a bridge fails. In Pittsburgh, the deterioration was visible, documented, and ignored. In Minneapolis, the flaw was invisible to every tool the oversight system had. Both bridges fell. The difference in failure mode does not produce a different outcome for the people on them when they do. The engineers who designed fracture-critical bridges were not cutting corners. That is worth stating clearly because the term sounds like a warning label applied after the fact. Fracture critical, as though someone should have known better. The designers of the I-35W bridge, the Francis Scott Key Bridge, and thousands of other structures built in the mid-20th century were working within the standards and the material economy of their era. Steel costs money. Redundant load paths require more steel. The engineering philosophy of the period optimized for efficiency, for the elegant transfer of force through the minimum necessary structure. The bridges that resulted were not defective. They were exactly what their designers intended. The problem is that they are still in service. A fracture-critical bridge, in precise engineering terms, is one that contains non-redundant steel tension members. Components whose failure will cause a significant portion of the bridge, or the entire bridge, to collapse, because there is no alternative path for the load to travel. In a redundant structure, if one member fails, the load redistributes. Adjacent members pick up the difference. The bridge sags or deflects or shows visible distress, but it does not fall instantly. In a fracture-critical structure, the failure of a single critical member removes the geometry that was holding everything in equilibrium. There is no redistribution, there is only collapse. In a 2014 analysis of the National Bridge Inventory, more than 20,000 bridges in the United States carried the fracture-critical classification. Of those, approximately 7,800 were both fracture-critical and in poor structural condition, carrying the double designation that engineers described as a significant combination of risk factors. A bridge that is deteriorating and has no redundancy is a bridge where the margin between current condition and catastrophic failure is narrower than in any other category. The Francis Scott Key Bridge in Baltimore was built in 1977. It was a continuous truss structure, a type that was common in that era, efficient in its use of steel, and fracture critical by design. The bridge spanned 1.6 miles across the Patapsco River at one of the busiest shipping channels on the East Coast, carrying more than 30,000 vehicles a day on a toll road that collected $56 million annually. It was the second longest continuous truss bridge in the United States. As far back as 1980, engineers had identified the bridge's fundamental vulnerability. A direct strike from a large vessel on one of the main piers would remove a primary support from a structure with no redundancy. The conclusion was documented. The Key Bridge, in engineering terms, could not survive such an impact. The warning existed in the record for 44 years. The Maryland Transportation Authority had a plan, a pier protection system, a fiberglass jacket around the water pier columns had been added to the capital program. Construction was scheduled to begin in 2029. At 1:28 in the morning on March 26, 2024, the container ship Dali lost electrical power and propulsion in the channel approaching the Key Bridge. The crew issued a mayday. There were minutes between the loss of propulsion and the impact. Enough time for authorities to stop traffic on the bridge, which is why the only people on the structure when it fell were 8 construction workers filling potholes in a closed lane. The ship struck the southwest pier of the main truss section. The bridge's continuous truss relied on the integrity of its complete structure. Removing the southwest pier removed a primary support from a system with no alternative load path. The south span fell, the central span fell, a northern span followed. The entire sequence, from the moment of impact to the completion of the collapse, took approximately 30 seconds. 6 of the 8 construction workers died, 2 survived. The Key Bridge was fully compliant with the building code at the time of its collapse. It had dolphin and fender protection around its piers, standard protection for its era, designed for the vessel sizes of its era. The Dali was not a vessel of that era. It was a modern container ship carrying 4,700 shipping containers of a class that did not exist when the Key Bridge was designed. The replacement bridge will be cable-stayed. That design is inherently redundant. Multiple independent cables carry the deck load, so the failure of any single element does not produce total collapse. The estimated cost is between $1.7 billion and $1.9 billion. The expected completion is fall 2028. The bridge that a $1.9 billion redundant replacement is being built to replace cost a fraction of that when it opened in 1977 was identified as vulnerable to vessel strike 5 years after it opened and stood for 47 years on a busy shipping channel before that vulnerability was realized. There are 309 other bridges in the United States that have been identified as having severe foundation deterioration, leaving them vulnerable to vessel impacts in similar fashion. Not fracture critical by design necessarily, but compromised in the specific way that matters when something large and uncontrolled strikes a pier. The fracture critical inventory and the deteriorating foundation inventory are not the same list. They overlap in places. Together they describe a category of bridges where the consequence of a single failure event is not a bridge that needs repair. It is a bridge that is gone. The design philosophy that produced these structures was rational for its time. The standards have since changed. Modern bridges are built with redundancy as a baseline requirement. The bridges that were built before that requirement exist in a different category. One that is not going away on its own, that is not addressed by inspection cycles alone, and that intersects increasingly with external pressures that the original designers had no reason to anticipate. Water moves as sand. That is the entire mechanism, reduced to its simplest form. When a river runs fast, during a flood, during a storm surge, during the kind of high water event that is becoming more frequent as precipitation patterns shift, it picks up sediment from the riverbed and carries it downstream. If a bridge pier is sitting in that riverbed, the water accelerates around the obstruction. The acceleration increases the water's capacity to carry sediment. The sediment at the base of the pier and around it and beneath it gets picked up and moved. The foundation that the pier was set into becomes shallower. The material the engineers assumed would be there, supporting the load of the bridge above, is somewhere downstream. That process is called scour. It is not dramatic in the way a collapse is dramatic. It happens below the waterline, out of sight, during the events. The floods, the high flows, when nobody is inspecting foundations. It is, according to research published in peer-reviewed engineering literature, the mechanism behind approximately 52% of bridge failures in the United States. More than half. Not corrosion, not design error, not overload. Water removing the ground a bridge is standing on. The bridges in the national inventory were designed for the flood frequencies their designers knew. A bridge built in 1964 in a river valley in Vermont was sized for the hydraulic conditions of that valley as understood in 1964. The expected flow rates, the 100-year flood elevation, the sediment characteristics of that specific channel. Those assumptions went into the foundation design. The depth of the pilings, the scour protection around the base, the clearance between the low chord of the bridge and the design flood level, all of it was calculated against a hydrological baseline that no longer exists. Climate change does not invent new failure modes. It changes the frequency and the magnitude of the events that trigger existing ones. A bridge foundation designed to withstand a 100-year flood is now experiencing what its designers would have called a 100-year flood on a shorter return interval. The scour that was supposed to happen once per century is happening more often. The sediment removal that the foundation was sized to survive once is being asked of it again before the river has rebuilt the material it removed the last time. Vermont is a specific recent example of what this looks like at scale. Heavy rainfall caused significant damage to an estimated 100 bridges in the state over a 2-year period. Not a single catastrophic event. A pattern of high water episodes arriving more frequently than the infrastructure was designed to absorb, finding foundations that were already aged, already past their design life in some cases, already carrying less reserve capacity than they had when they were new. Scour is the largest single mechanism. It is not the only one. Steel bridges are designed to move. That is not a flaw. It is an engineering feature. Steel expands when it heats and contracts when it cools, and a bridge that cannot accommodate that movement will develop stress concentrations at the points where movement is prevented. The solution is the expansion joint, a deliberate gap in the bridge deck, fitted with a mechanical assembly that allows the steel to slide or rotate as temperature changes. On a well-maintained bridge, the joint does its job invisibly, cycling through expansion and contraction with the seasons without transferring unusual stress to any structural member. On an aging bridge, the joint clogs. Debris accumulates. The mechanical assembly corrodes and seizes. The bridge that was designed to flex now cannot. When the temperature drops and the steel wants to contract, and the joint refuses to allow it, the contraction force has to go somewhere. It goes into the connections, the bearings, the members adjacent to the frozen joint. Elements that were not designed to carry thermal loads of that magnitude. The stress concentrates. Over years of seasonal cycling, fatigue cracks develop at points in the structure that the original engineer never identified as high-stress locations, because in a functioning bridge, they would not be. This is not a dramatic failure mode. It is a slow one. It adds load cycles to components that were not supposed to carry them, incrementally, winter after winter, until the fatigue life of that connection is consumed. The freight load problem sits on top of both of these. The trucks moving goods across the country in 2025 are not the trucks that the interstate bridges were designed for in the 1960s. The growth of container logistics, the pressure toward higher payload per trip, the evolution of vehicle configurations, these have produced a freight fleet that tests the load limits of bridges designed for an earlier standard. A bridge rated for the legal load limits of 1965 is not necessarily rated for the vehicle configurations that are common today. Weight restrictions on posted bridges are partly a response to this. An acknowledgement that the structure cannot safely carry what the road would otherwise permit. A bridge in good condition has reserve capacity. It can absorb an overweight truck, a severe flood, a frozen joint, without those events pushing it past its structural limits. The reserve capacity is the buffer. A bridge in fair condition has less buffer. One in poor condition has very little. The 49.1% of the national inventory currently sitting in fair condition. The bridges that have not yet crossed the threshold into poor, that are not yet in the crisis statistics, that are still carrying billions of trips a day without weight restrictions or closure orders. Those bridges are the ones where the compression of timelines matters most. The scour events are arriving more frequently. The thermal joints are older. The trucks are heavier than what the design assumed. The deterioration that was supposed to take another 20 years may now take 10. The bridge that was supposed to reach the top of the rehabilitation queue while still in fair condition may arrive there already in poor condition or may not arrive at all. The funding system that is already running behind is chasing a problem that is accelerating away from it. The Federal Highway Administration's most recent comprehensive estimate of what it would cost to address the existing backlog of highway and bridge investments in the United States was published in 2018. The figure was $1.1 trillion. That number is now 7 years old. The backlog has not shrunk in the intervening years. The bridges have continued to age. The deferred maintenance has continued to accumulate. The $1.1 trillion was the bill as of 2018. The bill as of today is larger, and no equivalent comprehensive federal reassessment has been published to say by how much. Within that figure, the bridge-specific rehabilitation backlog alone, the cost of bringing the nation's bridges to a state of good repair, not replacing them, rehabilitating them, is estimated at $191.3 billion. That is a separate accounting from the cost of outright replacement. The Federal Highway Administration estimates the cost of replacing every bridge currently in poor condition at $69.7 billion. Rehabilitating those same bridges rather than replacing them would cost $47.4 billion. Rehabilitation is cheaper. It is also time sensitive. A bridge that can be rehabilitated today for $47 billion cannot be rehabilitated for $47 billion in 10 years if it has deteriorated further. The cost curve for deferred maintenance does not flatten. It rises. The American Society of Civil Engineers, in its 2024 economic analysis titled Bridging the Gap, calculated a funding gap of $373 billion over 10 years. The difference between what current investment levels will produce and what is needed to bring the national bridge inventory to a state of good repair. That gap is not the total cost of fixing every bridge. It is the shortfall. It is the distance between the trajectory the current spending produces and the trajectory a healthy inventory requires. At the state and local level, the Pew Charitable Trusts calculated in December 2025 that accumulated shortfalls in net maintenance investment since 2004 have produced a deferred maintenance liability of approximately $105 billion for roads and bridges combined. This is a different measure from the FHWA backlog figure. It captures the gap between what states and localities have been spending and what depreciation models suggest they should have been spending. Compounded over 2 decades, the $191 billion and the $105 billion are not the same number describing the same problem. They are two different lenses on the same underlying failure to invest. The Federal Highway Administration has done the elimination math. To bring the bridge backlog to zero by 2036 would require $28.1 billion in annual investment in 2021 dollars. That is the rate at which spending would need to flow, sustained over more than a decade, to close the gap. The Infrastructure Investment and Jobs Act, passed in 2021, created the Bridge Formula Program, the most significant dedicated federal bridge investment in a generation. It channels $5.5 billion annually through fiscal year 2026, distributed to states based on their inventory of poor and fair condition bridges. The law also created a competitive bridge investment program for larger projects. $5.5 billion annually is roughly half of the $28.1 billion annual rate that elimination of the backlog would require. It is meaningful. Engineers and state DOTs have directed it at the highest priority structures. The number of bridges in poor condition has declined, slowly, in each of the years since the law passed, from approximately 44,000 in 2021 to approximately 41,685 in the June 2025 FHWA data. The trend is in the right direction. The rate is not. At current spending levels, the backlog does not reach zero. It shifts. The bridges at the top of the priority queue get addressed. The bridges below them wait. The bridges below those continue to deteriorate, moving from fair condition toward poor condition, joining the queue at the bottom while the queue above them moves slowly forward. The net inventory of bridges in poor condition declines, but the inventory of bridges in fair condition, the 49.1%, the nearly half, continues aging into the category below it faster than investment can address. The federal funding picture has since grown more uncertain. The current administration has pulled back on infrastructure commitments that Congress had approved. In 2025, the White House announced it would hold $18 billion allocated for transit projects already underway in New York City. Broader reviews of IIJA spending commitments have been underway, with states and localities uncertain about the federal funding they had planned around. The responsibility for infrastructure investment has been shifting towards state and local governments at the same time that those governments are confronting maintenance backlogs they did not create and cannot easily absorb. William Glasgow, a public finance advisor at the Volcker Alliance and one of the researchers behind the deferred maintenance analysis, described the position plainly. "The cliff is here," he said in October 2025. "The bridges aren't getting any newer. The water treatment plants aren't getting any newer." The cliff is not a future event. It is the present condition of a system where the investment rate and the deterioration rate are not moving in the same direction, and where the population of bridges most exposed to that gap, the 49.1% in fair condition, still carrying billions of trips a day, not yet in the crisis statistics, is the largest single category in the inventory. A bridge in fair condition preserved today costs a fraction of what the same bridge costs to replace after it crosses into poor condition and continues deteriorating. That arithmetic is not contested. Every infrastructure economist, every state DOT, every FHWA assessment agrees on it. Preservation is cheaper than replacement. Early intervention is cheaper than emergency response. The funding math does not currently produce early intervention at the scale the inventory requires. It produces a slower version of the same problem. A queue that moves, but not fast enough, chasing a deterioration curve that is accelerating away from it under the pressures described in the previous section, in a policy environment where the federal commitment that was supposed to close the gap is now uncertain. The bill exists. It has been calculated from multiple directions by multiple agencies using multiple methodologies. Every calculation arrives at a number that the current investment rate does not reach. The Fern Hollow Bridge reopened in December 2022, 11 months after it fell. A new structure, same crossing, same ravine, same Forbes Avenue carrying the same traffic between Squirrel Hill and Regent Square. The rebuilt bridge is sound. It will carry its 14,000 daily vehicles with a full reserve capacity of new construction on steel that has not yet begun to lose cross-section, on concrete that has not yet admitted its first chloride ion. The bridge is fine. That is worth saying plainly. What is not fine, and what the rebuilding of one bridge in Pittsburgh does not address, is the system that allowed that bridge to reach the condition it was in before it fell. The underfunded maintenance budget, the inspection contractors who were not following federal guidance, the city without enough staff to act on years of recommendations, the load rating calculations that were wrong. None of those conditions were invented in Pittsburgh. None of them were resolved by the collapse, or by the NTSB investigation, or by the rebuilt bridge that now carries Forbes Avenue over Fern Hollow Creek. They are the ordinary conditions of municipal infrastructure management in the United States, replicated across thousands of bridge owners, cities, counties, townships, special districts, each carrying a portion of the national inventory with budgets that have not kept pace with the aging of what they own. Somewhere in that inventory, right now, there is a bridge carrying a number. Not a dramatic number. Not a number that appears in a headline. A condition rating sitting in a database maintained by a state DOT, describing the current state of a deck or a superstructure or a substructure that has been deteriorating for years. The number is a 4 or it is a 5 that is trending toward 4, and it has been trending that way since the last inspection and the inspection before that and the one before that. There is a maintenance recommendation attached to it. There may be several. Whether those recommendations have been acted on depends on a budget process in a jurisdiction that is probably not thinking about that bridge today. That is where 49.1% of the national inventory lives. Not in crisis, not in the headlines. In fair condition, which is the technical term for a structure that is deteriorating on a trajectory toward the category below it, carrying billions of trips a day, waiting for an intervention that the current funding rate delivers too slowly to reach all of them in time. Consider the arithmetic of design life applied to a single bridge. A structure built in 1972, designed to the 50-year standard that governed mid-century bridge construction, reached the end of its design service life in 2022. No announcement was made on that anniversary, no sign appeared at the bridge approaches. No traffic was stopped, no inspection was triggered, no flag was raised in any federal database because a calendar date had passed. The bridge simply continued carrying traffic, as it had the day before and would the day after, now operating in the years its designers had not planned for, accumulating load cycles against a reserve capacity that was sized for a different number of them. There are thousands of bridges in that position right now. Most of them will be fine. The steel and concrete of a well-maintained bridge can carry load far past its original design life. The 50-year standard was a planning horizon, not an expiration date, and structures that have received adequate maintenance outlast it regularly. The qualifier is adequate maintenance. The funding math of the previous section describes what adequate maintenance would cost nationally, and what it is currently receiving, and the distance between those two numbers. The inspection system is what stands between those bridges and an outcome like Minneapolis or Pittsburgh. It catches visible deterioration. It generates recommendations. It produces the condition ratings that define what 6.8% and 49.1% mean in practice. It does all of this on a 24-month cycle, with the gaps that Pittsburgh demonstrated are real. Contractors who may not follow guidance, bridge owners who may not act on findings, load ratings that may not account for the steel that actually exists today, rather than the steel that was specified in 1968. The bridges that carry the most risk are not randomly distributed. They concentrate in the places where the funding is thinnest. The rural counties with the longest deferred maintenance queues, the mid-sized cities with the oldest stock and the smallest capital budgets, the states where the local bridge inventory has been underfunded for long enough that the fair condition category is full and the poor condition category is growing. The least funded bridges in the least funded jurisdictions are the ones where the gap between the maintenance recommendation and the maintenance action is widest, and where the gap between current condition and the condition that requires closure is narrowest. That is not a prediction. It is a description of where the inventory stands, derived from the data that FHWA publishes annually, that ASCE synthesizes every 4 years, that the Congressional Research Service has translated into the funding math that does not close. This morning, somewhere in the United States, someone drove over a bridge they have driven over 100 times. The commute was ordinary. The bridge did what bridges do. It held the road above the gap. It transferred the load into the ground. It allowed the crossing. It will do the same thing tomorrow and the day after that and the day after that. Most of the time, the number holds.